My name is Jacob Hilton. I'm at the Alignment Research Center, and this is joint work with my co-workers there. So the motivation for this work is the idea of deceptive alignment, which I'm sure many of you are familiar with, also known as scheming. Basically, current alignment techniques like reinforcement learning from human feedback are good at optimizing average case performance on distribution, but they don't really give us good worst case guarantees or distribution guarantees. And one particular failure mode we might worry about is an AI system that is paying attention to whether or not it's in training, and then if it has the capability to determine whether it's in training or not, it may sort of like behave very differently in a deployment situation. Maybe it's like pretending to be helpful in training and then takes the mask off, as it were. So in order to kind of study this problem from a theoretical perspective, we instead study this related problem of backdoor detection. So in backdoor detection, you have an ordinary training process, and then you also have an adversary who comes in and modifies that training process in some way. So a classic example might be they poison some of the data, so they replace a small fraction of the data with some nefarious data. And the attacker's objective is to produce a model which, in most cases, behaves exactly the same, but on some secret trigger that only they know, the model behaves differently. And so we kind of use this, so it might be like a secret password in the case of a language model or something like that. And we basically using this as kind of an analogy where the comparison with deceptive alignment is that the backdoor model and the ordinary model are required to be very similar on distribution. This is kind of analogous to the deceptive alignment case where on distribution, the kind of intended model and the deceptive alignment model are very similar. And basically what we're doing by sort of introducing this adversary by using backdoor deception is we're kind of making a worst case assumption about the training process. So in the paper, we introduced this formal game. So this looks a little bit complicated, but basically the first three boxes you should kind of think of as saying roughly what I said on the previous slide. So we basically set up, so in this formal game, the attacker kind of is just allowed to choose whichever function they like as being this kind of backdoored function. And their job, as I said on the previous slide, it has to be very similar to the original function, but different on this particular trigger. And then we also imagine there's a defender whose job is to basically tell whether the model has been backdoored. And in previous work, usually people consider, can you just statically tell, is this a backdoored model or not? We consider a slightly different version where we also give the model a particular input. So the defender's job is, given a model and a particular input, is this an ordinary model on an ordinary input, or is it a backdoored model on specifically the trigger? In the paper, we prove have two main results. So one is in the case where the defender does not have any computational constraints. So this is, in some sense, like an unrealistic assumption. But the point of studying it is that maybe it'll give us some insight into sometimes there are theoretical algorithms which are very expensive. We can maybe approximate them by cheaper techniques. So in that setting, basically we showed that the defender has a winning strategy using a kind of like regularization-based method under this like sort of technical assumption that sort of this technical assumption basically says how close the two models have to be. So that's maybe a positive sign, but then we also look at the computationally constrained case where the defender has to run a polynomial time. And in that case, actually the attacker has a winning strategy, which is less good news. But there's a silver lining, which is that the attacker's strategy kind of involves this cryptographic construction that involves like a secret key. And if the defender knew that secret key, then they could actually defend. And so maybe sort of like a high-level takeaway you might take away from this is, if the defender could see how the model was constructed, it could potentially like avoid this problem. And so the takeaway might be, if we're thinking about maybe models internal space methods for avoiding deceptive alignment, possibly like very productive thing to be doing is to be looking at the training data, looking at the model during training, and seeing like when this backdoor kind of gets inserted. And that's everything. Thank you.